All right, so we're going to continue looking at the laws of logarithms. So we've already developed what these laws are, so we're going to use them to simplify logarithmic expressions. So remember the product law says that log base c of m times n equals to log base c of m plus log base c of n. Remember the quotient law, log base c of m over n is log base c of m minus log base c of n. And the power law is that log base c of m to the p is p times log base c of m. And these rules can go from one to the other or backwards. It doesn't matter, right? And we saw examples where we would do that, going in one direction or the other. So again, those laws are there and they're on the formula sheet, so you don't have to memorize them. You just got to know how and when to use them. So these first examples ask us to express in terms of individual logs x, y, and z. So for the first one, because it's log of x times y on top, that would be log base 5 of x plus log base 5 of y. And then because it's being divided by z, you'd be minus log base 5 of z. So these laws work both ways. You can take an expression where you have different logs with the same base, adding and subtracting those terms, and you can simplify them into one expression, or you can expand the one expression out into a sum and or difference of terms like we did there. For question B, I would first write the radical as a power. Cube root of x is the same as x to the 1/3, and then the exponent comes in front as a coefficient, and we've written that one in terms of log x, which is what we're asked to do. Write it in terms of either log x, log y, and or log z. Question C, 1 over x squared would be x to the -2, and then the -2 can come in front using the power law. It'd be -2 log base 6 of x. So again, we've written that one in terms of log x. Question D, you would expand this out, but you'd probably do it in a couple steps. It would be the log of x cubed minus, and in the brackets here, we would have the log of y plus the log of the root of z. So that would be the first step, and notice I've used brackets there to keep the y and the root z together. If you remove the brackets, that would change all the signs inside. I guess the other thing we can do here is use the power law. That first term would become 3 log x minus log y minus the log of z to the power 1/2, and then the 1/2 can come in front as a coefficient. So last week we did examples where we had this final expression and we worked back into writing it as a single log. And remember, we put those last two terms in brackets, which changed all the signs inside to get that original expression. Well, you can reverse all that and work backwards like we just did there. Right? So we're going to do the same thing for these ones. Write them in terms of individual logarithms of x, y, and z. So because you're using the quotient law for this first one, when you break them up into individual logs, that involves subtraction. Remember, the laws of logarithms are connected to the laws of exponents. When you divide powers with the same base, you subtract the exponents, keep the base the same. So now when you're dividing, when you have a quotient involving a log, you subtract the individual logs with the same base. So they are connected. For question B, that is the same thing as the log of x to the half times y to the half. And now we can use the product law of logs and say this is the log of x to the 1/2 plus the log of y to the 1/2. And then the 1/2 would come out front using the power law. So you could look something like that. The other option here is that you could simplify a little bit by taking out a common factor of 1/2. And I forgot about the bases, so let's put those in there. So by taking out the common factor of 1/2, it would look like that. Again, you don't necessarily need to take out the common factor of 1/2, but perhaps it's something that they might do in an exercise that you're checking your answers in the book. Okay, for question C, because it's 9 over the cube root of x squared, this will be the same thing as the log base 3 of 9 minus log base 3. And instead of writing it as a cube root of x squared, you might write it as x to the power 2/3. And in this case, what is log base 3 of 9? What's log base 3 of 9? 2, because that's asking 3 to what power is 9. And then for the second term, use the power law to bring the coefficient to the front. Right, so now you've expressed in terms of log x. Question D. So the top, because it's x to the 5th times y, that's the product law. And then you're dividing by the root of z, so that's the quotient law. And then we might bring the exponents in front as coefficients. And there we've written them in terms of log x, y, and z. So you can expand a logarithmic statement to get an expression, and you can go backwards. You can simplify an expression into a single log as long as the bases are the same, which in this case they are. So the first two terms, because they're being added together, that's the product law. The last term is subtracted, so that's the quotient law. And you can do a little bit of simplifying here. 2 goes into 8 4 times. So you have the log base 6 of 4 times 9, which is 36. And Pinky, was log base 6 of 36 equal? Why? Because that's asking 6 to what power is 36. So we evaluated that one. Question B. Because it's log base 7 of 7 times root 7, we can use the product law to expand that. It would be log base 7 of 7 plus log base 7 of the root of 7, or 7 to the power 1/2. Using the power law, that second term can be written like that. Jonathan, what's log base 7 of 7? That's asking 7 to what power is 7. Or using the change of base identity, that would be the log of 7 divided by the log of 7. So in the same way, that second term will be half of 1, because that's half of log base 7 of 7. Log base 7 of 7 is 1. So it's 1 plus 1/2, which is 3/2, or 1.5. Right, question C, we want to write that as a single log and then evaluate. So it'll be log base 2 of 12 squared minus, so inside the brackets here, it'll be log base 2 of 6 plus log base 2 of 27 to the power 1/3. The coefficient comes up as an exponent, just like I did for that first term. So that's going to give us log base 2 of 144 minus, I can still do some work inside the brackets here because (27 to the power 1/3) means the cube root of 27, which is 3. Power 1/3 means cube root. So now I can simplify inside the brackets by using the product law. It'll be log base 2 of 6 times 3, which is 18. And now because I'm subtracting logs with the same base, I can use the quotient law. It'll be log base 2 of 144 over 18. And 144 divided by 18, is that 16? No, it's 8. So that's log base 2 of 8. Which is what, Lohita? What does log base 2 of 8 mean? Two to what power equals 8? Okay, all good. So again, we can use the laws of logarithms to simplify and evaluate. And then, as we've seen before, in many cases, not even having to use our calculator. So I would expand this by using the product law, because it's the log base 3 of 9 times root 3. That'll be log base 3 of 9 plus log base 3 of, the root of 3 is 3 to the half. What's log base 3 of 9 equal, Maha? That's asking 3 to what power is 9? So using the power law for that second term, the 1/2 comes in front. Brett, what's log base 3 of 3? Because that's asking 3 to what power is 3? Or, using the change of base, it'd be log 3 over log 3. So this is 2 plus 1/2 times 1. So it's 2.5 or 5/2. Okay? So you can see, I mean, there's no rule that says how you do these. You just want to simplify if possible. In the case of question A, by expanding, it allowed us to do it without really touching a calculator. In the case of question B, log base 5 of 1,000 would be irrational. Log base 5 of 4 would be irrational. Log base 5 of 2 would also be irrational. So in this case, I would try and combine them into one term using the appropriate laws. But first, I would put those last two terms in brackets with the minus sign in front, which changes all the signs inside. So this is something that we have done before. And so inside the bracket now, we can use the product law. Oh, log base 5 of 1,000. So we can use a product law to simplify those two expressions inside the bracket. That'll be the log base 5 of 4 times 2, which is 8. And now because you're subtracting logs with the same base, you can use the quotient law and combine those two together. And 1,000 divided by 8, I think, is 125. Yep. And log base 5 of 125 is 3. That's asking 5 to what power is 125. And remember, you can always use the change of base identity to evaluate these by going to log of 125, close the bracket, divided by the log of 5. That's one way to get it. If you have the newer operating system, you can do it that way. Log base 5 of 125. The other option, remember, is evaluating this the way we first started, by making it equal to x. We want to know what it equals, so let's let it equal x. And then you convert from logarithmic to exponential by starting with the base and cycling through. So that would be 5 to what power is 125. And you can write 125 with a base of 5, that's 5 cubed. So that's another reason why x equals 3. Right, so lots of different options to evaluate logarithms. You can also do it graphically if you wanted to. Right, once you write this statement here, oops, this one here, sorry, you could graph y equals 5 to the x as y1, y equals 125 for y2. Find the point of intersection. It would be at x equals 3. So lots of different options there. For question C, I would probably rearrange the terms to put the positive ones first, the minus one second. At the same time, I'll use the power law. So 2 log base 3 of 6 will be log base 3 of 6 squared, plus log base 3 of 2, minus 1/2 log base 3 of 64 would be log base 3 of 64 to the power of half. 6 squared is 36. And 64 to the 1/2 means the square root of 64. Square root of 64 is 8. And so now we can use the product and the quotient laws to combine these into one logarithm. So it'll be log base 3 of 36 times 2 over 8. That'll be log base 3 of 72 over 8, which is 9. And log base 3 of 9 is asking 3 to what power is 9. So that will be 2. Okay. So once again, we want to write them as single logarithms, but then also it says to state the restrictions on the variables. Remember, the restrictions come from the fact that you cannot take the log of a negative number, and you also can't take the log of 0. Okay? So for example, why can't you take the log of 0? Well, if you have log of 0, that's a common log base 10. If you want to know what that equals, let it equal x, convert from log to exponential by starting with the base and cycling through. This is asking 10 to what power is 0. Doesn't work. Okay? There's no number you can raise 10 to get 0 as the answer. So that's one reason why you can't take the log of 0. Also, the fact that the graph of a logarithmic function, remember, was the inverse of an exponential, right? The graph of an exponential function, if it was an increasing function, it had a y-intercept of +1, it went something like that. So it goes through the point 0, 1. So remember that a logarithm is the inverse of an exponential function. To get points on the inverse, you switch x and y around. So instead of going through 0, 1, it would go 1 through 1, 0. And instead of having the x-axis as an asymptote, the inverse would have the y-axis as an asymptote. So So this is what the graph of the logarithmic function would look like. That's the inverse of that exponential. It is completely on the right side of the y-axis. X can't equal 0 because there is no y-intercept, nor can x be negative. The graph shows us that. Okay, so these are the reasons why you cannot take the log of 0 or a negative number. So, again, we want to write these as single logarithms in simplest form and then state the restrictions. So the restrictions come from the argument, what you're taking the log of. And in each case, it's either the log of x or the log of x squared. So our domain here would be that x would have to be greater than 0 for these ones. But it's not always x is greater than 0 because sometimes the argument changes. Or you might have the log of x plus 2 or the log of x minus 3. That changes the argument. That'll change the domain. But when it's just the log of x, the domain will be that x must be greater than 0. But first, we're going to use laws of logs to simplify these. So in the case of these first two terms, it's the log base 7 of x squared times x, or log base 7 of x cubed, minus, so this 5 log base 7 of x over 2, I would write as 5 halves log base 7 of x. And then you can use the power law to bring the 5 halves up as an exponent. And now you're subtracting logs with the same base, so you can use the quotient law and combine them into one expression. It'll be the log base 7 of x cubed over x to the 5 halves. And now you're dividing powers with the same base, so you can subtract the exponents and keep the base the same. Because I have to subtract 5 halves away from 3, I want to express 3 with the denominator of 2 as well. So that'll be 6 halves. Take away 5 halves, which is 1 half. So you can write it like that, or bring the 1 half in front. And again, the restriction here is that x must be greater than 0. So these next ones, the domain's going to change. Okay? And we'll see what becomes of the arguments, because we're going to do some factoring here. But first, we will combine the two expressions together using, in this case, the quotient law. It'll be log base 5 of 2x minus 2 over x squared plus 2x minus 3. So there's a common factor of 2 on top. And on the bottom, x plus 3, x minus 1. And you factor them. So by doing this, you can see that the x minus 1s will cancel. So this simplifies this. And you're left with log base 5 of 2 over x plus 3. Now, for the domain, you've got really two different factors to look at, right? Two different factors that contain the variable x. One of them being x minus 1, the other being x plus 3. If we look at each of those separately and we say that x minus 1 has to be greater than 0, that would mean that x has to be greater than 1. But we also have a factor of x plus 3 that must be greater than 0. Therefore, x must be greater than negative 3. These are two conflicting statements, so we need to choose the one that satisfies them both. And that would be the first one. All values of x greater than 1 are also greater than negative 3. So that would be the domain for this one. That would be the restriction. X has to be greater than 1. You see, all numbers greater than negative 3 are not also greater than 1. So you have to choose the one that satisfies them both. Okay? So once again, we'll use the laws of logarithms here to simplify this. So for that first term, I would bring the 4 up as an exponent. And inside the brackets, I can use the product law. But first, I would bring the 5 up as an exponent as well. And now I can use the product law to simplify inside the brackets. That'll be log base 3 of x times x to the 5th, which will be x to the 6th. Now I will bring the 1/2 in front of that log base 3 of x to the 6th up as an exponent. So you're actually going to have x to the 6th to the power 1/2. And when you have one exponent raised to another, you multiply the exponents and keep the base the same. This will be log base 3 of x to the 4th minus log base 3 of x cubed. 1/2 of 6 is 3. And now we can write these as a single log by using the quotient law. It'll be log base 3 of x to the 4th over x cubed, which is just x to the 1 or x. And because all of the arguments are just x, x has to be greater than 0. Okay, looking at question B, this is again one we will have to factor. But first we'll write as a single log. Again, to simplify, we'll need to factor. The top is difference of squares. The bottom is a trinomial. That needs to be factored. So the x minus 3's would cancel, and you'd have log base 2 of x plus 3 over x plus 2. So there's a simplified expression, and for our domain, we have to look at all the different factors. Take each one separately. We've got a factor of x plus 3. That has to be greater than 0. So x would have to be greater than negative 3, just from that factor. We also have a factor of x minus 3 that must be greater than 0. So x has to be greater than 3 from that factor. On the bottom, we got a factor of x minus 3, which we've already dealt with. So we just have the x plus 2 that has to be greater than 0. So x has got to be greater than negative 2. Again, we need to take the statement that satisfies all of them, which is that x must be greater than 3. That is the one that satisfies all. All numbers greater than 3 are also greater than negative 3 and negative 2. Okay? Describe the transformations that need to be applied to the graph of y equals log base 3 of x to result in the graphs of the following. So now we're going back to our transformations. So we need to look and see what those different parameters are. How do these graphs, or how do these equations relate to y equals log base 3 of x? So to do it, I would expand this out. It'd be log base 3 of 243 minus log base 3 of x. And log base 3 of 243, well, that's asking 3 to what power is 243? I think that is 3 to the power 5. You can check it. Yes. Log base 3 of 243 is 5. So this will be 5 minus log base 3 of x, or negative log base 3 of x plus 5. So we've written the terms in the order that we're used to seeing them in. There's a negative 1 in front of the log base 3 of x. Remember, we're always comparing this to log base 3 of x. So that negative sign in front means that a is negative 1, which means you're going to have a a reflection about the x-axis. And then you've got a k value of positive 5, which means the graph is going to shift 5 up. So compared to y equals log base 3 of x, this one will be reflected over the x-axis and shifted 5 units up. Those are the transformations that we would need to apply in order to transform it from log base 3 of x. So for question B, we'll do something similar. So that 9x squared, well, that's the product law. It's 9 times x squared. So it's log base 3 of 9 plus log base 3 of x squared. Log base 3 of 9 is 2. That's asking 3 to what power is 9? Plus 2 log base 3 of x. Or we can write it as 2 log base 3 of x plus 2. So that it's written in the order that we're used to seeing it. So in this case here, we have an a value of positive 2. Which means the graph is going to be vertically stretched. About the x-axis. By a factor of 2. And again, we have a k value of positive 2. Which, It's being vertically stretched. So the distance at each point is from the x-axis is multiplied by the stretch factor. So it's vertically stretched about the x-axis. If there's a horizontal stretch, that's about the y-axis. So k value of 2 means the graph is going to be shifting up 2 units. These next examples, there have been questions on diploma exams in the past that look like this. We're told that log base 2 equals a, and log of 2 equals a, log of 7 equals b. Write an algebraic expression in terms of a and b for each of the following. The first one, log of 2 on 7, using the quotient law, we need the log of 2 minus the log of 7. Using the quotient law, expanding that out. And we're told the log of 2 is equal to a and the log of 7 is equal to b. So now that expression in terms of a and b is a minus b. Question B, using the product law, you'll have log of 7 plus log of the root of 2, or 2 to the power a half. The 1/2 can come in front as a coefficient. The log of 7 is b plus 1/2 log 2, which is a. So that would be b plus 1/2 a. Now for question C, if we use the quotient law, this would be the log of 49 minus the log of 16. But we need to write them in terms of log 2 and log 7. So log 49 would be the log of 7 squared, and the log of 16 would be the log of 2 to the 4th. We have to write them in terms of log 2 and log 7. So we can write them in terms of a and b. But before we do that, the exponents come in front as coefficients. So now log of 7 is b, so this will be 2b, take away 4 times a, because log of 2 is a. Okay? So we're going to stop there for today. You can work on these questions. I will post the solutions to Google Classroom so you can check your answers. Remember that assignment from Wednesday, or Tuesday? That was page 35 in your package. Most of you handed it in already. But if you haven't done that, you need to get that handed in. Okay? So work on page 400, 401. I will post the solutions to Google Classroom so you can check your answers.